Question 1. So, for part A, I've got to solve the equation fg of x equals x. So I need to put x into the g function first of all, and then put that output into the f function and set that equaling to x. So popping x into the g function, well obviously that's what I've got here, 4 over x minus 2, and then I substitute this into the f function. So this goes into this. So I get 7 lots of 4 over x minus 2 minus 1 equaling x. So then multiply by 7 gives me this. Add 1 to both sides gives me this. Multiply both sides by x plus 2 gives me this. Multiply out the pair of brackets. Gather the like terms of the x's in the middle. Take away 28 from both sides, and I've got a quadratic to solve. This factorizes to x minus 6, x plus 5 equaling 0. So my two solutions are x equaling 6 and x equaling minus 5. Now for part B, it says hence or otherwise find the largest value of a such that g of a equals the inverse function of a. Now there's only one mark going for this, so there's got to be a quick way of doing this. And really you've just got to look back at part A and say if you basically inverse function both sides, you're going to end up with this. So the solutions for part B are going to be the same as the solutions for part A. So our solutions for A are going to be 6 and minus 5. Then obviously the largest value is 6. Now if you didn't spot the hence method, and you wanted to do it or otherwise, you can obviously just crunch through the algebra. So we first of all find the inverse function of A by changing the subject of the function, giving us our inverse function of x being x plus 1 over 7. Then we set that equaling g of a, and then we basically get back to the same position here. So we're in exactly the same situation as we were for part A. So again we get the two solutions. Question 2. So to differentiate this division, we need to use the quotient rule. So our u is our numerator, which is 4x, and v is our denominator, which is x squared plus 5. So differentiate both of these to get this. And our dy dx is going to be v du dx minus u dv dx all over v squared, which is this. Then multiply out the numerator and gather like terms, and we end up with this as the final solution. Now for part B, we've got to find the set, hence find the set of values for which the differential is less than 0. So this has got to be less than 0. Now in order for that to be the case, clearly the numerator has to be less than 0, because our denominator is going to be squared, which is always going to be positive. So we just need, for this to be less than 0, we need our numerator to be less than 0. So 20 minus 4x squared has got to be less than 0. Add 4x squared to both sides, divide by 5, and we get x squared being greater than 5. Now when we square root this, so just think of our quadratic graph. If we want it to be greater than 5, we need x to be less than minus root 5 to pick up these set of values here, but also x to be greater than root 5 to pick up this set of values. So that's our final solution. Question 3. So for part A, we're going to use the cos A plus B trig identity. So cos A plus B equals cos A cos B minus sin A sin B. So we line that up with what we've got to express, and we can see that our r cos alpha has got to equate to r2, and our r sin alpha is equating to the 1. So r sin alpha equals 1, r cos alpha equals 2. So if we divide 1 by 2, that gives us tan alpha being a half, so alpha equals 26.57 degrees. And then if we square 1 and we square 2 and add them together, we get r squared equaling 5, so r equals root 5. Remember, that comes about because when we square each of these, we get r squared sin alpha squared plus r squared cos alpha squared, and of course sin squared alpha plus cos squared alpha equals 1. So for part A, our answers are alpha equal 26.57 and r equaling root 5. Now for part B, we just set it up using our answer to part A. So we have our denominator, we replace the 2 cos alpha minus sin alpha minus 1 with our answer from part A, which I've done here. Then multiply both sides by the denominator, multiply through by 15, add 15 to both sides, divide by 15 over root 5, and we get cos alpha plus 26.6 equaling 17 over 15 root 5. So if we go and choose to let capital X equal theta plus 26.5, changing our boundaries, we get our first solution for cos x equaling 59.5 degrees. Then using our all silver toy cars within our revised limits, we get solutions for big X as being 59.5 and 300.5. Then adjust these back to theta by taking away 26.6 from each of these, and we get final answers of theta equaling 33.0 and 273.9 degrees. Now for part C, the only difference is this change of sign here. Okay, so it's the change of sign up here. So rather than r sin alpha equaling 1, r sin alpha is now going to equal minus 1. That has a knock-on effect of tan alpha being minus a half and alpha being minus 26.57 degrees. Again, the knock-on effect as we sort of go through the process of part B, so we've now got cos alpha minus 26.6 rather than plus 26.6, and again right at the end, so again following it all the way through, the change of sign impacts on this. So rather than it being 59.5 minus our 26.6, we're now just adding our 26.6, giving us a solution of 86.1 degrees. Question 4. So for part AI, we need to find the y-coordinate of the point A. So this is when x equals 0. So substituting x equals 0 into the g function, e to the 2 lots of 0 is 1. So 4 lots of 1 is 4. 4 take away 25 is minus 21. So the modulus of this is plus 21. Now for part AII, the exact x-coordinate of the point B. So that's when y equals 0. Alright, our y step is 0. So we set our function to equaling 0. So 4 to the e to the 2x minus 25 equals 0. So add 25 to both sides and divide by 4. Square root this gives us e to the x being 5 over 2. So x equals ln 5 over 2. Now for part 3, the value of the constant k of this asymptote. So basically just think about as x gets progressively negative. Okay, so we're going to have e to the progressively negative power, so that's approaching 0. So this first term is approaching 0. 0 minus 25 is minus 25. Modulus thereof is 25. Now for part B, we've got to solve where the function equals 2x plus 43. So e to the 4e to the power of 2x minus 25 is equaling 2x plus 43. So adding 25 to both sides, dividing by 4, we get this. If we then go and ln both sides, we get 2 ln e to the x equaling ln a half x plus 27. Obviously, yes, and then power rule, that's 2x ln e. Obviously ln e equals 1, so 2x equals ln half x plus 17. Divide through by 2 and we get what we needed to show. Now for part C, we just start off to find x1 by substituting in x0, which is 1.4. So we substitute 1.4 into the iteration formula. giving us 1.4368 to 4 decimal places. If we then take our x1 value, but the unrounded version, this one, substitute that back into the iteration formula, that gives us x2, which is 1.4373 to 4 decimal places. Now for part D, choosing a suitable interval show that this is the root. We basically take the upper and lower bound of this. So if we go and take 1.4365 and substitute that into the iteration formula, and then secondly the upper bound, the 1.4375, we'll see that there's a change of sign. With the first we got a solution which was negative, for the second we got a solution which is positive, so we could then say the graph of y of f of x crosses the x-axis between these two bounds, so there is a root between these two bounds. Question 5. So for part A, we need to differentiate this using the product rule. So u is e to the 3x, v is cos 4x. So obviously differentiated, that gives us du dx being 3e to the 3x and dv dx being minus 4 sin 4x. So dy dx is u dv dx plus v du dx, which is this. We then factorise, taking out the e to the 3x, we get this. Now e to the 3x cannot equal 0, so it's going to be our bracket equaling 0. So we set this equaling 0, so 3 cos 4x equals 4 sin 4x. If we then divide by cos 4x, we get 3 equaling 4 tan 4x. So tan 4x equals 3/4. So if we go and choose to let big X equal 4x, our first solution for big X is going to be 0.6435. Remember to revise our boundaries, so our boundaries for big X are 4 lots of our boundaries for lowercase x, so our pi and 2 pi. So our first solution was 0.6435. Now that's obviously not within our criteria. Our solution that we're picking up is this one round here, which is pi plus 0.6435, which is 3.785. So converting this back to lowercase x by dividing by 4, we get our single solution, our answer being 0.9463 to 4 decimal places. Now for part 2, we've got x equaling sin squared 2y, which of course is sin 2y all squared. So if we differentiate this, so dx dy equals 2 times sin 2y times the differential of the bracket, which is 2 cos 2y. And then factorising that, taking out the 2, we have 2 lots of sin 2y cos 2y. Now using the double angle formula, which obviously derives from here, we can say that sin 2a equals 2 lots of sin a cos a. So sin 2y cos y is sin 4y. So that's the big step here. So dx dy is 2 lots of that. Now just flipping that over, inversing that, we get dx dy being 1 over 2 lots of sin 4y, which is half cosec 4y. Question 6. So for part A, we start off by doing the algebraic division. So when we divide through, we get x squared plus 3 with a remainder of 4x plus 12. So our solution is x squared plus 3 plus the remainder still to be divided by the divisor. So x squared plus 3 plus 4x plus 12 all over x squared plus x minus 6. Now this third term factorises to 4x plus 3 and x minus 2x plus 3. The 2x plus 3 terms cancel out, giving us a final answer of x squared plus 3 plus 4 over x minus 2. So our A is 3 and our B is 4. Now for part B, hence or otherwise using calculus find equation of the normal to the curve with this function at the point where x equals 3. So we're going to need to differentiate the curve. So let's sort of get it ready to differentiate. So take the x minus 2 upstairs. So we've got 4 lots of x minus 2 to the power of minus 1. So when we differentiate this, we get 2x minus 4x to the minus 2 to the power of minus 2. And then let's take the x minus 2 to the minus 2 downstairs, so giving us for our second term minus 4 all over x minus 2 all squared. So there's our differential. We need to find the equation of the normal at the point where x equals 3. So substituting 3 into the function, we can see that the gradient of the tangent would be 2. So therefore the gradient of the normal is minus a half. Now we want to use our y minus y1 formula, so we know the gradient's minus a half. We know the x value, so our x1 is going to be 3. We just need to work out what our y1 is. So we need to substitute our x1 into the function. So let's substitute it into this version of the function. So substituting 3 into this, which I've done down here. So that gives us our y1 being 16. So we can now use y minus y1 equals m x minus x1, y minus 16 equals minus a half x minus 3, or versions thereof. Question 7. So for part A, let's just start off by thinking about our normal sin graph. Okay, so if we think about it between pi over 2 and minus pi over 2, when x is pi over 2, our y value is 1. When x is 0, y is 0. And when x is minus pi over 2, our y is minus 1. Now for our arc sin graph, the coordinates just flip over. So rather than being pi over 2, 1, we get the coordinate 1 pi over 2. Obviously 0 to 0 flipping over is still, just changing places, is still 0, 0. And here we go from minus pi over 2 minus 1 to minus 1 minus pi over 2. So our graph looks like this. Another way to think of it is think about when we sin pi over 2 we get 1. So if we inverse both sides we get pi over 2 equaling inverse sin 1. So when we've got x being 1 we inverse sin it, we get pi over 2. And the same with minus pi over 2. Sin minus pi over 2 is minus 1. Inverse sin both sides, we get minus pi over 2 equaling inverse sin minus 1. So when we've got x being minus pi over 2, when x is being minus 1, when we inverse sin it, we get y being minus pi over 2. So that's the shape for 7a. Now for part B, we've got to find the exact value of x for which this equals 0. So 3 lots of arc sin x plus 1 plus pi equals 0. So take away pi from both sides and divide by 3. We get arc sin x plus 1 equaling minus pi over 3. We sin both sides. We then get x plus 1 equaling sin minus pi over 3. And the sin of minus pi over 3 is minus root 3 over 2. Take away 1 from both sides. We get x equaling minus 1 minus root 3 over 2. Question 8. So for part A, let's just focus on the left hand side. So we've got cot 2 cot 2x plus tan x. So that's 2 over tan 2x plus tan x. Now we're now going to be manipulating the tan a plus b formula. So really the double angle formula. When a equals b, we can say that tan 2a equals 2 tan a all over 1 minus tan squared a, and flipping both sides over we can get 1 over tan 2a equaling 1 minus tan squared a over 2 tan a. So we can basically substitute in, at this point we can say, rather than this is 2 lots of 1 over tan 2x, it's 2 lots of this. So that's the big step for part A, going from here, where this is 2 lots of 1 over tan 2x, to being 2 lots of this. Now the 2's then cancel, and then really we've just got to get a common denominator. So at this point we choose to multiply the second term top and bottom by tan x. That allows us to then add our numerators, so we just get a simple 1 on top, 1 over tan x, which is cot x as required. Now for part B, let's start off on the left hand side. So we've got 6 cot 2x plus 3 tan x rather. We then factorise that, we get 3 lots of 2 cot 2x plus tan x, and that takes us back to our part A, so we can say that that's in fact is 3 cot x. So our left hand side is 3 cot x, so we're saying our left hand side 3 cot x equals our right hand side cos x squared x minus 2. Now this is the big step here. This is just one of the ones you need to learn. You need to learn that 1 plus cot squared theta equals cos x squared theta. So we can replace, if we break this down to being cos x squared x minus 1 rather than minus 2, we can replace the cos x squared x minus 1 with the cot squared x. Then this becomes fairly straightforward. So we've now got, having replaced this with this, we've got 3 cot x equaling cot squared x minus 1. We can rearrange that, making it equal to 0, and we've just got a quadratic to solve, with a being 1, b being minus 3, and c being minus 1. So this gives us the solutions, cot x being this, so flip both sides over. We get tan x equaling 2 over 3 plus or minus root 13. When we plus the root 13, we get our solutions for x of 0.294 and minus 2.848. And when it's we're minusing the root 13, our two solutions are x equaling minus 1.27 and 7 and 1.865. Question 9. So for part A, so use the model to find the amount of the antibiotic in the bloodstream 4 hours after the dose is given, and the dose was 15 milligrams. So D equals 15 and T is going to equal 4. So substituting that in, we get x equaling 15 times e to the power of minus 0.2 times 4. Popping that into our calculator, we get 6.740 milligrams to 3 decimal places. Now for part B, show that the total amount of the antibiotic in the bloodstream 2 hours after the second dose is this. So basically 2 hours after the second dose is 5 plus 2, so 7 hours after the first dose. So just looking at it from the first dose point of view, the effect from the first dose point of view, we're going to be substituting in t being 7. So that's going to be 15e to the power of minus 0.2 times 7. And then the effect of the second dose after 2 hours later, so plus 15e to the minus 0.2 times 2. So 7 hours from the first dose, 2 hours from the second dose. Add these together, we get what we had to show. Now for part C, we're looking at this from the point of view of t hours after the second dose is given, and we need to find the time for the amount of antibiotic in the bloodstream to equal 7.5. So basically, from the point of view of the second dose, we're saying it's t hours after the second dose, and then from the point of view of the first dose, it's going to be t plus 5 hours. So this is from the second dose, this is from the first dose, and these two together are going to give us an amount of antibiotic of 7.5. Okay, so from the second dose, from the first dose, 5 extra hours. So it's then rather just some quite complicated algebra really. So obviously, so just multiplying this out here, we're going to get 15e to the minus 0.2t times e to the minus 1. Minus 0.2 times 5 is our minus 1. We're then factorising, so we're taking 15e to the minus 0.2t out from both of these two terms, leaving us with 1 plus e to the minus 1 in the brackets. We're then dividing through by 15, and then we are lunning both sides. Then multiplying by minus 5 takes us to this. We're then multiplying out the denominator to give us this, and then we're popping the numerator over both terms in the denominator. So that's minus 5 ln a half plus e over 2, and then basically then just flipping them over, we're then getting 5 lots of ln 2 plus 2 over e.